done with the correction. So that to waste an entire class. So the last time as quiz one I'll take maybe 20 or 25 minutes extra on Thursday. The class will be from 12 to 1:50 instead of 12:50. So I want you to make note of that. So then let's begin with the assignment. Assignment 6. So let's first take this derivation. I think the second one. We had similar ones like this for the pure component, which I didn't really look at in detail. This might be a more complicated one. So let's see how to. So the first thing is obviously to look at the definition that you must know. Once you know the definition, what we have asked is the logarithm, so it's easier to handle that directly. So this would be logarithm of ezi plus by RT. This is what we have now. This I want to differentiate with respect to temperature. Right? So can someone come and do it on the board? Can you come to the board and this differentiated with respect to temperature, and obviously you have to make use of certain formula that we have derived earlier. So first term, what would it give? Differentiate with respect to temperature, giving P and mole fraction states. First term, what would it give? 0, very good. So plus, then we have to handle this. Yes, times and then plus 1 over RT. Yeah, plus 1 over RT times the derivative. Yes, so now we want to get H, the partial molar property of the ith component, partial molar enthalpy of the ith component. So let's take it as it is. What is this? We have the formula for that. If you recall, we derived it. Suppose I take Vg into minus SdE. Because Vg I will continue, but I want to just point out. So from here, we show that d mu j for any mixture by dt dN of dz is what? Minus the partial molar entropy. When it is under this formula, for the pure component will be just negative of the specific entropy. Now it will be the negative of the partial molar entropy. So we have finished it. So how would you write this in terms of partial molar property, the first term? It is a Gibbs free energy partial molar property, right? No, it's not mu type. So just play around with the notation, right? You should understand chemical potential as a Gibbs partial molar Gibbs free energy. The chemical potential is always X. Very good. Yeah, minus the same for the mixture, the ideal gas, and then plus 1 over RT times. The first term would be negative of the partial molar entropy. These probably have to keep in mind. Same with the derivative with respect to P. It would be simply the partial molar volume. Yes. PM. Yeah, so you should be very clear what you are writing. This is the partial molar property. Just don't get carried away with the notation. What they are, because you get a ds by dni. We interchange the order of differentiation. You have to remember those formulas. Yes. Now you have to combine the two. Right? So you can take 1 over RT squared out, and then you will get the answer. Yes. EIPM mix minus T times. Yes. So you've got the answer. This is HIPM. Ideal gas mix. So that's fine. Yeah. That completes it. So good payout. You have to know the final answer is given. So you have to recognize that this is the Gibbs free energy and this is going to give you the partial molar entropy. So that should be sufficient. And this is true. It's not just because G minus Ts is H that you can immediately conclude that G IPM minus TSAPM is the enthalpy. But you can clearly see that this comes from the fact that D equal to H minus Ts. And everything I can express in terms of P and N. And this also in terms of P and N. So when I differentiate with respect to Ni, giving P, N, K not equal to I, so I will get the answer. And so this is Pi Pm. And so if I do the same thing, I will get HIP. Because I am taking the temperature phase, the temperature figure it to be, you should know that this follows directly from the this relation. So the relation between G, H and S also carries over to the partial molar property, because I am just differentiating with respect to Ni, giving T and P fixed. Right? So that is,
There should be positive sign.
so there's a positive sign in this case.
G plus Ts.
Oh, okay. Yeah, that's true. Yeah, because you're taking minus 1 over RT squared, right? So that's true. You have to make sure there is a minus 1 over RT squared. Yes, T plus T. So there is a minus that you have taken out. So this will give T plus T. Yeah, that's true. That's a good point. I didn't notice that. Yeah, it is T plus Ts. So what we have is G. So this is correct. So from this we conclude that HIPM, so any mixture is GI that takes care of that. So are there any questions? You can very easily do the other part. is the partial molar volume. Doesn't even require it. It's direct. You don't even need to combine two terms. You will automatically get it, I guess, when you differentiate with respect to P. You get a term from here also then. And you have to see, I don't want to get into it, how you are going to get the answer. But you have to get that. These are famous relations. The analog of these relations for the pure component we have already seen, though we didn't derive it there. But clearly, if you are able to do it for the mixture, you should be able to do it for the pure component as well. We will do the numerical parts of the assignment. What I will do is, even though you are asked to calculate fugacity for component in a mixture for the reddish form and the Ben-Lawrence, and the formulas are available in the standard textbook, so you can go and look at the formula and try to derive them. So I don't want to go through the whole thing. We plan it for the van der Waals, and the derivation is very similar. The only thing you have to understand, what I want to point out is this R-K, which we haven't introduced so far. It is somewhat, it's a special case of the SRK. It is often used in books because it simplifies the calculation. So the notation is slightly different from what is there in the book. So I'm treating A as a constant. So basically this is a special case of the SRK where alpha RK, we will call this as alpha. So the alpha, instead of somewhat more complicated, 1 plus whatever kappa times this, here it's a simpler version of the SRK. So there are no additional parameters in this. It's simply 1 over TR power R. Right? So it's very much like the SRK but simpler. But when you are applying it to the mixture, the calculation of B mixes, but we have already seen for the A mix, you have to take the A and the alpha together. So maybe I can define a new for all the cases where there is a temperature dependence. I can write this as A times, I introduce a new, because many folks simply write this as A of T, it's A times alpha of T. It's very confusing because on the one hand, you have A which is a function of temperature. The same symbol is used for a constant, so I can regard this. But when you apply the mixture rule, A alpha mix, this is for pure component, you can say. Because we saw that A mix is sum over I into 1 to C, sum over A into 1 to C, A I J, Z I Z J. But the Z I's are the mole fractions, not the compressibility factor. So when you apply it to this, so you have to apply this, I think, like this. So this would be A alpha ij. Right? So I want you to pay some attention. Go to the books and then see if this matches with what I'm pointing. Because I'm not going to go through it in detail in the class. So A alpha. So if I want to write this for a mixture, how is Aij different? For van der Waals is very simple because A is independent of temperature, and we said that this is this. Because none of the books discuss this in great detail. So you might want to check some of the standard textbooks and see how they handle this. So this is very simple because A, both the pure component A is just A. There is no other additional factor and I can do it. But when I want to apply the mixture rule to a case where we have A alpha of temperature, which is A times an alpha. So now we have an alpha for each component, which is going to be different, right? Because the alpha has as a parameter the acentric factor, which is different from different substances. So the mixture rule now has to be applied the product A times alpha together, right? So this could actually appear A mix alpha would be I'm sorry, This is what it is. A alpha mix, and how is A alpha ij defined? Again, square root of A alpha I times A alpha j. So I have to calculate A times alpha of t for the ith component times A times alpha of t for the jth component. Each one will be. So if you want to write it like this, now you see that this is square root of ai aj. You want to distinguish it from the way we handle the van der Waals. It would be alpha I of t times alpha j of t. So depending on the temperature, this factor is now going to change, right? So I want you to, because the answers are given, maybe because of problem from YBC law, so you can take a look at the problem. But what I want to do is to simply do it for the van der Waals, for which also I have some answers, and you can check the answers. So I'm going to calculate the same familiar ethylene, because we have some of the numbers there. Ethylene-propylene, if you recollect, we consider this mixture. The main problem is I have the volumes calculated somehow for these two cases using the van der Waals. So since I don't know, the volume calculation is the main thing in this. Unfortunately, I didn't have the time to do the same for the very strong and the big problems. Since you can probably do it faster. So ethylene-propylene, we consider a process by which, so I have done it for both these states. We saw that this goes from 323 Kelvin 10 bar to 600 Kelvin and 16 bar. So I can just take this as an example and calculate the fugacity of each component in the mixture for these two conditions. Just forget about what the enthalpy change or enthalpy change for now. So if I take this for instance, I have to look at the van der Waals. It's important to write the formula in a way that is easier to calculate. So if you look at the formula for the logarithm of any component in a mixture, and the mixture is regarded as following the van der Waals equation state. So this is for the van der Waals. So you have RT log B gas mixture, I can simply write this as A. So this is the loading formula. This we have derived in the class. So the formula for, you just treat this as A alpha, because there's not going to be any differentiation with respect to temperature. dP by dNi that you have to calculate, right? And so you have to do that for the reduced form. So we'll see, maybe you can try that and we'll see if there's any complication we can do. Now van der Waals is much simpler because the A is independent of temperature, but that is not going to be a problem for the fugacity. The entropy and some of the functions, you get dP by dt, then you should know how to differentiate the A alpha mix with respect to temperature. That might be a bit complicated, but that's not going to be a big part here. So I can now rewrite this as the R-K logarithm of saying this is now the compressibility factor plus minus 2 over this is an R. log 5, then there is no RT. The RT log, so we check the formula. RT log 5 is what I wrote probably partially. So log 5 will just have everything divided by RT, and so I'll get this. So minus 2 over B RT. So now you can see that I can cancel this log set with this log of z and write it as no RT here also. So I can write this as minus log of z minus b x plus bi times the inverse of z minus b. Z minus, and then I have minus 2 over BRT sum over, and that log set will cancel. And here we have Z1, which is ethylene, is 0.7, and Z2, this is no more, so I will make it Y1. So this is how there is what you have the formula, then it's simply tedious numerical calculation. Then the B mix is B mix times P over RT, and BI is BI times P over RT. Okay, so if you now look at this is calculated for both components, it's the same, for I equal to 1 as well as for I equal to 2. This calculation is the same. BI obviously will differ depending on which component you are looking at. And this also will differ. So let's now do this case for the 323 Kelvin and Z bar. Right? So what I have here is A1 is 0.453 Newton meter per 4. A2 is 0.845, same unit. And B1 is 5.7 into 10 power. And B2 is 8.25 into 10 power minus 5. The volume has been calculated for this condition, 323 volume. That is the most important calculation. Approximately I have calculated it to be 2.537 into 10 power minus 3 B2 per mole. That's the volume of the mixture, specific volume of the mixture. So from this I can calculate A mix is not really needed actually. I don't need A mix, but B mix can be calculated to be 6.5 into 10 power minus 5. So that is just B1 times Z Y1, which is 0.7. B2 times Y2, you will easily verify. Now, capital B mix turns out to be is simply B mix times P over RT, and that is already visible. That is 0.0242, and Z, all everything is for the mixture PV by RT turns out to be 0.9447. So now you have to be a bit careful. This B1, so we want to calculate log 5.1 mix. Then I need B1, separate this, or once I have Z and then B mix, I can easily calculate the difference and also the logarithm, the difference inverse, and then also the logarithm. So that part will be useful for both the components. Now B1, for component 1 I have to calculate B1. So B1 would be simply B1 P by RT, and that turns out to be 0.0212. And the B2 would be B2 P by RT, and that turns out to be 0.0307. And you have to be careful again about this. two components. Right? So what would it be for phi 1? You can calculate. So this is what would this will depend on the I is different for 1 and 2. So that we have very clearly remembered. What is it that distinguishes one component from another? Is the I. So Bi is different and this is Aij. Everything is just this other, all the other indices that appear are summation index. Right? So for here, what I need is sum over k equal to 1 to 2. A1j yj. What I need here is k equal to 1 to 2. A2j yj. Just use the formula, but we should know how to handle this. So this will be A11 y1 plus A12 y2. This is all now the notation. As per the notation Aij is simply square root of Aiaj. So A11 is clearly only A1 and A12 I have to calculate is square root of A1 A2. Right? So A1 is given. So square root of A1 A2 I have to calculate. That turns out to be also I have to calculate it. Very straightforward calculation will lead to 0.6187. Same unit, Newton meter per 4. So, and here this would be A21 y1. Of course, A21 is equal to A12 because of this formula. Right? Whereas A22, which is A2 y2. So you will clearly see that this would differ for the two components. If you know clearly which are the same, so you don't have to keep calculating it again and again. You can keep separating and then use it for the two components. So when we put all this together, what I am getting, you can verify this, is that phi 1 is turning out to be 0.9592 and phi 2, all of the mixture, 0.9182. So they are quite close to 1. That's amazing. So the composition factor is also close to 1. They are more towards the idea of towards looking like an ideal gas mixture. And when I go to here for this condition, using the same van der Waals equation stated, what I have here, phi 1 mix is 0.962 and phi 2 mix is 0.907. So I don't know what to make out of this, the difference between phi 1 and phi 2 for the two states. But clearly, this is what we see today. And the important thing you need is that the V here, which I have approximately calculated, to be equal to 7.9 times 10 to the minus 4 meter per square. You can do this numerical calculation for yourself. You can recalculate the volume, maybe even more accurately, and then get these answers. But they will be somewhat similar. But if you know how the whole formula is structured and how to calculate these mixtures, some of these are mixture quantities, some of these like the I are pure component properties. So you should know how to distinguish and how to calculate them. So this step is not needed. You can directly do with this. This is I think more convenient. Might require a bit more calculation, but then you're dealing with numbers which are of the order of 1 rather than 2 point something to 10 to the minus 3 and so on. Right? So I think this is probably what most of the books do. Are there any questions? Right? So when you go to R-K equation of state, very common sense, the formulas are available directly, so you can go and use them. The R-K, I don't know how many books give the formula, you ask to derive the formula. So it will be fairly straightforward, and I want you to go and try to do it. Because the answer, numerical answers are given, you can verify whether you are getting them. Are there any questions? question is something which we have considered about the phase rule, right? So clearly, for the parts 1 and 2, where either nitrogen or oxygen dissolve in water, right? So you can treat them as one component. Whereas for the third case, water vapor in the gas phase, N2 and O2 both dissolve in water, so they have to be treated as individual components. So the number of components would be different, right? And so you can give the answers to this, but I want to more carefully look at, write down all the equations and count the variables and unknowns, and then make sure the formula is always C minus pi plus 2. So number of components for 1 and 2, parts 1 and 2, so if water vapor is there and air is there, and water is there, CO2 is there, air is there. The number of components will be 3. You can easily figure out what the degree of freedom will be, 2 phases. Whereas for the third part, the number of components will be 4. So it will be 1 degree of freedom more. But there is still a difference between parts 1 and 2. Even though for both of them the degree of freedom will be 3, there is still a difference because in one of the cases water vapor is not present in the gas phase, in another cases it is present, water is present. So you have to distinguish and see the difference in the 3 cases. Right? So I leave you to do that because we have already discussed it. Now the fourth problem is to do with humidification. I will only point out the use of the terminology is what you should know. The humidity, molar humidity, what it means in percent saturation. What we have here is the basic equation is this. So you can distinguish between the Ravi's. This is a special case of the Ravi's law. The liquid phase is basically pure water. So this is the basic idea in humidification. But what you are given though is you are given that in a particular case, YW by YA, this is the molar absolute humidity. So it's basically the ratio of the 2 mole fractions is given to be 0.04. So what can you say? So you have to understand that this is 1 minus YW. So from this I can get YW to be 0.04 by 1 plus 0.04. It will be slightly different from 0.04 because the value is so small, there will hardly be any difference between the mole ratio and the mole fraction. But things might change if you have something of the order of 1.1 or something, then it will be different. So you can clearly see that this is what I have. So I have to substitute it here at 1 atmosphere, 760 times YW 0.04 by 1.04 is, or I can take the logarithm because what is given is the logarithm of PW sat of water. And so if I take the logarithm, then I can directly substitute. The logarithm is given to be 18.3036 minus 3816.44 by T minus 46.13. Now there are 2 things you should know that the Antoine's equation is given in different forms. Now this is somewhat non-standard form. The standard form, you would have the logarithm to the base 10 and this temperature would be in centigrade. But here it is given temperature is in Kelvin and this is the natural logarithm. So it depends on when you consider a reference for I don't know what is PSAT. PSAT is in mmHg. So that's very important. That's why I put 760 here. That's very important. I forgot to mention that. In this formula, PSAT is in T is in Kelvin. And I have 3 important things you should know. Whether the logarithm is given as base 10 or natural logarithm, what are the units of PSAT? Typically it is mm mercury, which means 760 is equal to 1 atmosphere. That's the thing that you all are familiar with. So if that is in mm mercury, and T here is in Kelvin. Okay, so can you tell me now what the answer is for T? Just calculate and so the answer that you will get will obviously be in Kelvin, but if you make sure that the pressure, because this is both units of pressure, and this logarithm is given, the logarithm given, you normally don't associate a unit with any quantity, you take the logarithm of, but this is how it is tabulated. So whatever is within that quantity obviously has to have units, because it refers to the saturation pressure, and here it is given that it is in millimeter mercury. So before you do anything, you should put both sides in the same units, because we know the right hand side refers to pressure in units. So here is where the pressure appears, and you given this to be 1 atmosphere. So I have to convert this before I take the logarithm. That is very important to know. Right? And now you will get the answer directly in Kelvin, whereas the formula has been given in terms of centigrade, then you will get the answer in centigrade. Yes, what is the answer? 301.78 Kelvin, right? So that's approximately 28.63 degrees. So now in the next part, you are given that you can add water mixture at the temperature calculated. Now this corresponds to 100% saturation. Right? So now you are given that you have 760 ml, and you also have whatever you calculate, 28.63 degrees centigrade. But now the mixture, air water mixture, is at only 80% saturation. 80% saturation. What does percent saturation mean? It is 80% of the saturation molar ratio, molar humidity actually. Right? So we have already calculated that. This is capital YW. This is the saturation. Because we have told that mixture is equilibrium here. So this is saturation. And look at 80% of this. This is to make you think about the difference between the what is termed as percent saturation and the relative humidity. And so percent saturation is 80%, so which means the actual YW is 0.8 times, which is 0.8 times 0.04. Now you are asked to find what is the mole fraction of the water in the mixture. So YW actual, so here everything is saturation. That's something you have to know. Whereas here the actual YW would obviously be 0.8 times 0.04 by 1 plus. So this is roughly maybe 0.3 here, 0.03. 0.031. I mean, this is 0.032. And this will be very different from, because it's almost, the denominator is almost close to 1. This turns out to be about 0.031. So not much different. But the question now is, what is the relative humidity? Relative humidity and percent saturation are different. Relative humidity, we call it as alpha, relative humidity. Is simply YW by YW saturation. It's the ratio of the mole fraction, whereas the percent saturation, as it is called, is the ratio of the mole ratio, or the ratio of the humidity. The humidity is nothing but, the molar humidity is nothing but the ratio of the moles of water to the moles of air. That is what is often used as a mole ratio, rather than a mole fraction. So alpha, you have to calculate, it is also going to be close to 80%, 0.031 divided by whatever you have here. YW saturation is 0.0385. that is what is it? That, and that turns out to be 0.81. It's actually 81% related to humidity, whereas it is 80% saturated. It's not the best example maybe to bring out the difference between the two, but you should know that there is a difference. Typically, air water mixtures usually are very dilute in terms of water when you deal with humidification, right? So, because of that, there's not much difference. But 80% saturation in this case actually corresponds to slightly higher relative humidity. So the two are different. But in terms of the degree of saturation, they are both the same. It's the same mixture that I am talking about. But the way it is measured with respect to saturation, there are two measures. One which compares the actual humidity with the saturation humidity. The other which compares the mole fraction of water with the saturation mole fraction. So this is what we have. Okay. This is 80% saturation. Good question would be, for instance, where would this lie? If, for instance, we are plotting, the mixture at a particular pressure or temperature to the 80% saturation. So we can, for instance, ask, I'll leave it as an exercise for you to find out what is the dew point temperature. It's something you would want to calculate, right? So the best way is to put it in a picture. So if I have, let's say, fix the pressure, just use the picture and P versus Y. They now are going to fix pressure. We're going to cool the mixture. To recollect the definition of dew point curve, to cool the mixture, maintaining the same humidity out of contact with water. Then at what point it will start condensing out of the mixture. So if I look at this, now Y versus T, how would it look like? The fixed pressure Y will increase with temperature. So if you make it something like this, now let's say it is 100% saturation. So what we are having here is this particular mixture, right? Let's work in terms of we can put capital Y. So if I want to plot it, it's always important to understand these concepts. So always plot it on a diagram, then you know what we are talking about. Viewpoint is easier to see in terms of the diagram. So saturation. So let's plot this. So I have 0.04. Right? The temperature is 28.63. So I can mark 0.04. Temperature is 28.63. Now I am at the same temperature, but 80% saturation only. Right? So this curve is going to be at 80%. Passing the origin, so it's not connected. So 80% would be everything is 80% saturation. So if I plot in terms of the percent saturation, 80%. If I plot in terms of mole fraction, I would choose the relative humidity. Right? So 80%, let's say I have that curve, would look something like this. So how do I get this? At every sorry, I think we messed up the. So it should be like this. Let's plot it. I don't know what kind of diagram I had earlier, but probably we had Y versus temperature. Then it's easy to draw vertically. So what I'm going to draw is YW versus temperature. It will still be increasing. So I'll have this saturation 100%. So here, that would describe the process of cooling, because that's, I don't recollect what diagram I had, but I have a feeling that I got the temperature on the x-axis. So I want to retain it. This is the standard way in which it is done. Right? So this is saturation, so if we want 760, we want to generate this curve 760 mm, and we're going to fix pressure. If we want to generate this, obviously I will choose different values of YW, right, and find the corresponding temperature, or easier maybe choose different temperatures and find the corresponding YW. So if I'm using this equation, then it is always saturation. There are no factors, right? So now we want to consider 80% saturation at each temperature. I know this is 100% saturation, so 80% will be 0.8 with plotting capital Y. So I can get that curve. So now the original mixture, let's say, corresponds to T equal to 28 degrees centigrade. So 28, let's say this is 28.63 or whatever we call, right? So this would correspond clearly to 0.04, and this is 0.8 times 0.02, 0.032. So if I want to calculate the due temperature, obviously I am looking at this temperature. So when will this become saturation? So what you have to figure out what you have to do. Clearly the dew point temperature would be lower than this. So we are cooling this out of contact with water. That means I am following this procedure. So when will this 0.032, which at 28.63 is at 80% saturation, when will it become 100% saturated? So I now choose this as the 100% saturation value and calculate the corresponding temperature. Right? So 0.8 times this. So of course this is now a mole ratio. This equation is in mole fraction. We have to convert it back and get the YW. So we want this, which is 0.031 as opposed to 0.0385. That now has to correspond to a saturation mixture, because at 28.63 it is only at 80% saturation. So I take this value 0.031 and substitute it here. The temperature that I will get has to be lower than 28.6. That will be the dew point temperature. You have to understand that that is what I have to do to calculate the dew point, what is known as the dew point temperature. I hope you can follow it. If you don't follow it, we'll take it up in tomorrow's class, but you have to see what we mean by dew point is 80% mixture by cooling is going to become saturated progressively, right? More and more saturated. When will, at what temperature, sufficient cooling, can it become 100% saturated to what we want? And I know that the 100% saturation curve is this. So for this value of the humidity or the mole fraction of water, which will satisfy this equation, I have to find the corresponding temperature, and that would be the dew point. If we run out of time, so we take up the